Hi everyone, this is Spectre P and we are Spectre AI. In this video, we focus on one of the most foundational aspects of quantum security, why security proofs fail. This video will cement the previous 18 videos in the series, and you will better understand the sequence of the curriculum. Quantum security is often described as provably secure, but real systems don't fail on paper. They fail in practice. In this video, we'll see why security proofs break down when physics, hardware, and the real world intervene. Security proofs live in a perfectly controlled world. They assume devices behave exactly as specified, noise is well behaved, and adversaries follow strict mathematical rules. But real hardware doesn't operate inside proofs. As systems leave the page and enter the physical world, precision fades. What was provably secure in theory becomes uncertain in practice. Proofs describe models, not machines. This is where security actually breaks. In real hardware, errors don't stay independent. Calibration drifts and introduces bias. Timing, power, and optics start leaking structure. And as protocols repeat, small deviations are amplified. Nothing looks broken, but security margins quietly erode. Attackers don't look for randomness. They look for patterns. In real systems, side channels introduce repeatable bias. Measurements aren't neutral, they leak information. When protocols respond to that leakage, feedback loops form. Small deviations get amplified. Over time, noise collapses into structure. And that structure is exploitable. Security proofs assume fixed, rule-bound adversaries. Real attackers adapt. Let's look inside what a security proof actually says. We start with a theorem, an idealized one. Let pi be a quantum key distribution protocol running over an authenticated channel. The proof begins by making a set of assumptions. First, that devices implement the protocol exactly as specified. Second, that measurement noise is independent and identically distributed. And third, critically, that no side-channel leakage occurs beyond the modeled quantum channel. Under these assumptions, the proof claims that for any adversary, the mutual information between the final key and the adversary's information is bounded by a negligible value epsilon, meaning the adversary learns essentially nothing about the key. But now, look at what happens in real hardware. In practice, the adversary's information is not just the quantum channel, it is the channel plus side-channel information such as timing, power, optics, and calibration drift. That means the total information leakage splits into two parts, what the proof models and what it does not. Security proofs only bound the channel term. They say nothing about the side channel term. And once that term is non-zero, the conclusion no longer holds. So the math is not wrong, but assumption number 3 is, security proofs describe models. Real attackers exploit machines. Here's what this graph is really telling us. On the blue curve, we see the security proof behaving exactly as advertised, the theoretical leakage term epsilon of n shrinking asymptotically as the system size grows, which is why proofs confidently label it negligible, but real systems don't live on asymptotes. They operate at finite scale, and that's where the dashed line comes in, representing a fixed hardware leakage floor from side channels like timing, power, optics, and calibration drift, which does not shrink as n increases. So, while the proof term keeps getting smaller, the total leakage curve flattens out and stops improving, meaning that beyond a realistic system size, security is no longer controlled by the proof but by the hardware. And this is the key disconnect. Cryptographic proofs bound only the modeled channel, not the physical implementation. So something that is provably negligible on paper becomes operationally dominant in real machines, which is why treating negligible as zero is not just optimistic, but dangerously misleading in practical quantum security. The phrase provably secure sounds absolute, but it isn't. Security proofs are conditional statements that only hold if every assumption in the model is satisfied exactly. In theory, those assumptions feel reasonable, but real systems violate them quietly and continuously. Hardware drifts, calibration shifts, components age, and side channels emerge in ways that never appear in the math. Attackers don't break the mathematics. They exploit the assumptions the math depends on. As systems scale, confidence increases because the proof looks stronger, while actual security erodes because the physical implementation diverges from the idealized model. That's the real danger of the phrase provably secure. It creates certainty where only conditional safety exists, and it hides failure modes that don't announce themselves until it's too late. Security is not a property of a proof, it's a property of an entire system. A security proof can only certify an abstract model, not a real implementation. In practice, the actual attack surface is defined by hardware, firmware, timing behavior, optics, calibration drift, and physical interactions that no equation ever fully captures. Protocols sit between theory and reality, but they inherit weaknesses from both sides. In the real world, the weakest physical layer dominates the threat model, not the strongest mathematical guarantee. That's why security doesn't emerge from equations alone. It emerges from interactions across the full system stack. And because of that, trust must be measured continuously, not assumed once by a proof. This is what actually works in real systems. Security is not something you assume because a proof exists. It's something you measure continuously. Proofs are valuable because they inform design decisions, but they do not validate real-world deployments. In practice, hardware, firmware, timing behavior, and optical effects define the true attack surface, not equations on paper. Real systems require constant monitoring, calibration, and verification as conditions drift over time. And most importantly, side channel risk is never eliminated. It is managed, constrained, and mitigated throughout the lifetime of the system. That is the difference between theoretical security and operational security. Here are the key takeaways. When we say provably secure, we're talking about mathematical models, not deployed systems in the real world. Real security depends on how hardware actually behaves, not how equations assume it behaves. Side channels turn tiny theoretical assumptions into real, exploitable vulnerabilities, and leakage that is considered negligible on paper often becomes material once systems are built and scaled. Security is not something you prove once and forget. It has to be measured continuously, monitored over time, and validated against reality. In practice, true protection doesn't come from a single proof, but from system-level design, ongoing observation, and the ability to adapt as real-world behavior inevitably diverges from theory. Thank you for watching. If you found this useful, please like the video and subscribe to the channel. It really helps us keep building deep, real-world quantum security content. You can visit spectreai.ai to explore over 55 hands-on quantum security labs and learn by doing, not just by theory. If you're interested in going deeper, you can also find our books on Amazon. And finally, leave a comment and let us know what you'd like to learn next. We read them all. Thanks again, and we'll see you in the next video.